So, image generation walkthrough. So, in this video, we builds directly on what all of the already learned about the diffusion models in the previous video. Since we already understood the training pipeline, um, we'll focus actually on how the image, I mean, how what happens during image generation. So when you read the prompt like a futuristic city at sunset, stable diffusion does not draw immediately. Instead, it performs the pipeline from the text prompt. We have the tokenizer and clip text encoder. Of the text encoder, we have the text embeddings. We have the random noise, that's the latent, and unit plus scheduler, and we'll repeat this process from 20 to 50 denoising steps, and we will have the clean latent and VAE decoder, and finally we have the final RGB image. So we use the diffusers library. One of the code we have used is from the stable diffusion pipeline. So it's from the diffusers and from the Hugging Face library. So what does that actually mean? Instead of writing hundreds of lines of code, we simply use stable diffusion pipeline, which already contains everything. Think of it like without pipeline, we have we will do manually the prompting, the tokenizer, from the clip, the text embeddings, generate noise, the unit, and scheduler. And we repeat this from 20 to 50 times. And then you have the VA encoder, decoder. Finally, you have the image, RGB image. So we would have to code every one of those manually. And the Hugging Face library pipeline does the code of pipe, the prompt, the images, and zero index, and performs everything automatically. So what is a pipeline? So we call it a wrapper. Okay, so a wrapper means an object that hides many complicated operations. Imagine analogy about the washing machine. Inside we have the water pump, motor, heater, sensors, but we only press start. So a stable diffusion pipeline is exactly like that. Inside it there are tokenizer, clip, unit, scheduler, VE, safety checker, image decoder. So we never manually connect them. Next is choosing the model. So like stable diffusion to base. So we use the stable diffusion to base instead of the stable diffusion 3.5, because stable diffusion 3.5 is larger, slower, requires permission, consumes more virtual RAM, whereas stable diffusion 2 base is faster, is smaller, and beginner friendly. Next is reload the model. We usually see stable diffusion pipeline that from pre-trained, so on. So several arguments are added, like torch the type torch.float16, which means we use it because it is 16-bit floating point numbers instead of 32-bit. Why? Because float32 is consumes out of memory, but the float16 almost half the memory. So little effect on quality. That's true, because modern GPUs are optimized for float16. Next is variant FP16. This is simply tells the Hugging Face load the FP16 version of the weights. Instead of 7 gigabytes, we might load 3.5 gigabytes. Next is cache DAR. Without cache, every run we download the model again, download the model. With cache, we download it once and save locally, and reuse forever. Next is generator. This is one of the most important ideas. Stable diffusions always start from random noise. That's correct. That noise is created by torque the generator. Example, we have the noise A, it produces the cat sitting, and a different noise is noise B, produce cat standing. Same prompt, different starting noise, different image. Next is SID. So the code is generator.manual SID, and the side of it is 123. Acidic fixes the randomness. Instead of random noise, it becomes always using noise number 1 to 3. Now everyone starts from the identical noise. Therefore, same prompt, same SID, same images. Here's an important detail. If you do the torch the generator that manual SID 1, 2, 3 inside of the argument and generate image 1, image 2, and image 3 without resetting, they become different. Why? Because the generator behaves like random number machine, from the current position 1, from 2 to 3 to 4 and 5. Even though it started at 1 to 3, it keeps moving forward to produce the exact same image. Reset the SID before each generation. Next prompt example. Example prompt is a cyberpunk samurai. So the pipeline performs from the prompt, the tokenizer, and clip, and embedding. Exactly like what we have learned before. Those embedding guides every denoising step. Next is num inference steps, one of the most important parameters. Example 20 steps. So the pipeline from noise, step 1, step 2, step 3, and so on and so forth until we have the step 20, and we have the image. If we increase it from 50 to 100 to 150, the unit predicts noise more times, more refinement. So more steps, more detail, longer generation. Next is num images per prompt. Example, we set it to number 4. So one prompt is a red dragon becomes noise. We have the noise A, that's dragon A, noise B, dragon B, noise C, dragon C, noise D is dragon D. Same prompt, different random latent, different composition. Next, guidance scale. Classifier free guidance, probably the most misunderstood parameter. Imagine our prompt says blue sports car, and if you have the low guidance, so in the model say I'll be creative, so there's a low guidance, we set to the low guidance, model says I'll be creative. Maybe we have the blue SUV, blue truck, blue sedan, and if we set it a high guidance, the model say I will obey blue sports car. And very high guidance, say we have blue sports car, blue sports car, blue sports car. Again, everything's blue. It begins to overfit the prompt. Images may look unnatural, oversaturated, distorted, exactly the way it is. Next is negative prompt. Instead of saying draw this, you also say don't draw this. Example, if you prompt the beautiful portrait and we set the negative prompt is blurry, low quality, extra fingers, deformed hands, crop. So our models will try to avoid those concepts during denoising. This became popular because every early stable diffusion version struggled with hands. Next is intermediate denoising. The structure in the previous videos, we have the callbacks. Instead of waiting until the images begins, we can inspect every denoising step from noise to step 1, step 2, step 3, and so on and so forth until the last step. A callback allows us to have step 1 PNG, step 2 PNG, step 3 PNG until step 3 PNG, and the last steps. This is exactly extremely useful for research, debugging, visualization, and education. Why does it look like an image of steps? This is probably the most important new concept. So, stable diffusion does not denoise RGB pixels. Instead, it denoises latents. So from the in the previous videos, we have the image, we have the encoder, and then have the latent space. Then unit works after that, and then we have the clean latent, and by decoder to the RGB, and finally we have the image. So the unit never sees RGB pixels, it only sees compressed latent representations. That's why intermediate outputs often looks like color blobs, fuzzy shapes, abstract features. Instead of gradually sharpening polygraphs, those colorful blobs are decoded versions of the evolving latent that the actual data unit operations on. Why we use the latent space? Because images are huge. Example, RGB image of 1024 by 24 by 3. That's approximately 3 million numbers. If we use the latent, we have the 128 by 128 by 4. It's only 65,000 numbers, much smaller. So the advantages are faster computation, less GPU memory, larger image becomes practical, training becomes much more efficient. This is why diffusion is called the latent diffusion model. So here's the complete image generation pipeline. So from the prompt, next is tokenizer. From the tokenizer, we have the clip text encoder. And next, we have the embeddings in the vector space, and then we random seeded it to have the same exact random value, and then we generate or perform the generator and apply the random Gaussian noise latent and repeat for specific inference steps. And then we fed it to the unit and predict noise with the scheduler. Remove the predicted noise gradually, update the latent, and repeat. And then we gradually remove it, and then it will become cleaner and cleaner, and there's final clean latent. Then we have the VAE decoder, and then the final RGB image. So training, the unit learns to predict the noise added for a latent at different time steps using the prompt embeddings as guidance. And then generation, the trained unit trains starts from pure random latent noise and repeatedly predicts and removes noise until a clean latent is produced. VAE is the VAE encoder is used during training to convert images into latents, while the VAE decoder is used during generation to convert the final latent back into an RGB image. And then the scheduler doesn't generate image itself. It determines how much predicted noise to remove at each denoising step based on the diffusion schedule. So the highlights here is the pre-built stable diffusion pipeline and how parameters such as the seed, number of inference steps, guidance scales, and negative prompt and callbacks affect the generation process, while keeping the underlying diffusion pipeline the same.